We are in section 5, working with circles. We're going to continue on with the equation of a circle and coordinate geometry and focus on tangent lines. First example, we're asked to find the length of AC here. If we zoom into this picture, we don't really have any detailed information on finding that. We do know that we have a triangle here, and it's a 5 on one leg and 8 on the other. The question is, we don't know that angle there. If it's a right angle, we could solve that. Whenever we have a line that is tangent to a circle, and remember that a line that is tangent to a circle touches at exactly one point, so if I were to continue that on, that would touch at exactly one point on that circle there, we will always form a right angle with a radius. And so if A is the center of the circle, then this 5-inch line is a radius. And so the radius and the tangent line will form a right angle every time, no matter where they connect. Since we then have a right triangle, we can just use Pythagorean Theorem here. So we can do 5 squared plus 8 squared is equal to our third side squared. 25 plus 64 is going to equal 89. And if we square root both sides, then our third side, our unknown side, is going to be the square root of 89. Moving on to our next one, this gets a little bit tricky, but also uses symmetry to help us out. We want to find the perimeter of this quadrilateral here. Now, we know that if we go from the center of circle Q here to the edge at point D where we have a tangent line, we will form a right angle. We can also form a triangle by drawing all the way out to that corner. Conveniently, we can do the same thing on the other side here. We can draw a radius out to here, form a right angle, and continue forming these triangles all the way around the circle. And whenever we have a tangent line, we're going to have a right angle. So if I fill in my picture here, you can see I have the 4 lines that touch the tangent points, and then I have 4 lines that form triangles in between each of those quadrilaterals. Now I'm going to look for some interesting symmetry here. Since I have a shared side, I know that these two sides are exactly the same. I also know that these two sides here are exactly the same because they're both radii of the same circle. And then I know that I have right angles in these triangles. So by that, I have HL congruence. The important part here is not focusing on the fact that it's HL, but the fact that these two triangles are completely congruent, which means that this side here is the same as this side here, meaning this is going to be 8. And by the same logic, we're going to have a right triangle where these two are the same. We have these two overlapping parts, and we have right angles once again. So again, by HL, these two outer parts are exactly the same, making AH over here 4. And if you're catching on to the symmetry, we can work our way around. If this piece here is 3, then this piece here is also going to be 3. And if that piece is 3 and this is 6, this is going to have to be 3, so that 3 plus 3 equals 6. And if that's 3, then this over here has to be 3 to match up with that other one. And now we've made our way all the way around the shape. So you can see we've got our 3's, our 3's, our 4's, and our 8's. The perimeter is just going to be adding all those numbers together. So 4 plus 4, we have 8. 8 more 16, 8 more 24. Add 6 more to 30. 6 more after that, 36. So our perimeter here is 36. Continue that pattern. We're going to find x in this picture. We have circles, and we have lines that are tangent to the circle, meaning that we form right angles here with those lines and a radius of the respective circle. Same thing here. Go to the outsides. We can draw a radius and then form a right angle. That means that we have shared side, we have same length legs, and we have right angles, meaning that these two sides, I'll draw these in different color, these two sides here are the same by HL. Take a similar approach to the other side. We know that if we draw a line in the middle, that is a shared side. We have radii that are going to be equal in length, and we have right angles. It means these two triangles are the same, which means these two lines here are going to be the same. The key here is that if this is the same as this, and this is the same as this, that they are the same as each other. So we can take these two values here, and we can actually set them equal to each other in this situation. So 6x plus 5, or plus 15, should be equal to negative 2x plus 37. Whenever I have that, I add 2x to both sides, and I subtract 15 from both sides. This leaves me with 8x is equal to 22. Divide both sides by 8 to get x alone, and this side looks like we can reduce it to 11 over 4 if we divide top and bottom by 2. So it doesn't always come out to be something clean, but 11/4 would be our answer. And then the next problem, we're again finding x. This time we have a triangle in the circle, and we know that we have a right triangle. We know this side and this side. And you might be thinking, we don't actually know this whole first side that I just highlighted because we're missing this part of it. Well, that's true initially, but we have to remember that if this is a circle and this is the radius, this part over here is also a radius. So this part over here is 12, making the entire side length, 12 plus 8, equal to 20. So our entire side length is 20, our other side length is 12, and so we would do Pythagorean Theorem to solve for our missing side. We remember that our right angle is down here at the point of tangent with the line coming across, and we are missing one of the legs. So we're going to do 12 squared plus our leg squared is equal to 20 squared. And when we do that, we get 144 plus x squared equals 400. We subtract 144 from both sides, and that leaves us with 256 for x squared. And when you square root both sides, that comes out to x is equal to 16. And if you recognized it earlier, this is actually just a variation of the 3, 4, 5 triangle. If you multiply 3, 4, and 5 all by 4, you will get 12, 16, 20.